Good morning or good afternoon, depending on where you're joining us from today. This is Mike Mazzarese. I'm a senior engineer with AST Environmental, and the presentation today will be focused on the BOS 200 technologies and treating petroleum hydrocarbon plumes and source areas, and we'll get into NAPL treatment as well a little bit. All right, sorry about that. So asking questions, I'm sure in these in the crazy time that we're living in right now, most of you have been on more webinars than you can count. But if you have not asked questions on previous webinars, if you see on your little taskbar on the right, you'll see the little question mark, ask a question, and if you type that down below, that'll go in, and we've got a couple of my colleagues are moderating the questions. Presentation should run about 35 minutes, and then we'll do about a 10-minute Q&A at the end. If we do not get to all of the questions, if we run out of time, we can certainly circle back with you. We know who asks which questions. So this is the fourth webinar in our spring 2020 series, again focusing on BOS 200. The previous three, so the first one was really kind of an overview, a primer on activated carbon. That was given by Scott Nolan, president of RPI. Second was given by Aaron Peacock with Microbac, talking about the synergies between activated carbon and bioremediation. The third one last week was given by my colleague Derek Pizarro, and that was focused on the BOS 100 and CAT 100 technologies for chlorinated solvent remediation. All of those are recorded, so if you would like copies of that, please reach out to me. My contact information will be on the last slide, and I can get those to you. This webinar is going to be given in 3 hours from now for the West Coast lunch time frame. And then the last 4 in the series are going to really focus on, we'll do a deeper dive on some of the topics we're going to touch on today. So the RDC, the Remedial Design Characterization, is going to be the focus for next week, and that's our name for the high density sampling that we do. And again, I'll touch base on that today. Webinar 6 and 7 are going to really focus on the applications and talk about overburden, challenging geologies on May 12th. A week later, we're going to focus on fractured bedrock. So that one's going to have slurry injections into fractured bedrock, but it's also going to touch base on adapting the overburden RDC procedures that we're going to discuss today. So we don't really talk about fractured bedrock much today. And then lastly, at the end of May, before we all kick off summer, we'll be talking about permeable reactive barrier design and installation. So RPI is the sponsor of this webinar series. I'd like to thank them, and it's a company that developed these technologies that we talked about last week on the chlorinated side, as well as this week on the hydrocarbon side. And they also operate what we call our project support laboratory, which I'll be referring to throughout the presentation today. And there's their website if you want to go ahead and check them out. In the lower left, so AST Environmental, the company that I work for, we're charged with project assessment and design for all of the trap and treat projects in North America and Europe and mostly around the world. We're also in charge of the field quality control as well. And we also launched a new website in the last few weeks, and astenv.com. So please feel free to check that out. And then lastly, the third leg of this RPI Group stool is our authorized installer network. And so AST Environmental, we're an installer of the trap and treat technology. That's how we kind of grew into this role as the distributor. But we have companies that we've partnered with in the US and internationally to be able to provide proper equipment and field staff with the proper training to be able to implement these technologies efficiently and properly. All right, so our footprint covered most of the US, most of Canada. Most of the work that we've done in Europe has been in Scandinavia, but as you'll see down below, we've also done work in UK, France, and Italy, and South Africa as well. Puerto Rico is actually pending. That work was supposed to be done already, but due to the current circumstances, that work was put on hold and will actually happen later this summer. So we'll touch base on the technology first, and then we'll do an overview of the RDC process. Again, that's going to be the focal point of the webinar next week. And then we'll talk about applications. So again, I'm not going to touch base on fractured bedrock much, but we'll get into overburden injections as well as the pre-drill process. And I'll give you one example of a PRB, but again, those are going to be the focal point of our subsequent webinars in this series. And then we'll wrap up with some project summaries and then finally some Q&A. All right, so first, this is the umbrella term that we use for all of these activated carbon-based technologies that RPI provides, is their trap and treat technologies. And so the vast majority of our projects are petroleum hydrocarbons, which will be the focus for today, and chlorinated solvents. So chlorinated ethenes, ethanes, methanes like carbon tet were discussed last week. So the activated carbon, which is the core similarity between these different technologies, gives us a very wide applicability range from concentrations, and we'll talk about geology here in a second. But from a concentration standpoint, technologies can be used from the distal end of a plume, where maybe it's a candidate for a PRB application, say double, triple digit ppb type concentrations. All the way back to the source area where you're dealing with saturated soil mass in the thousands of milligrams per kilogram, getting into the NAPL range. And so I guess just to take one small step back to talk about carbon a little bit. And so first thing is, when you're evaluating technologies that are activated carbon based, there's a couple things you need to keep in mind. One is the box you have to check is to make sure that they're not using regenerated carbon. I think most companies aren't, but I think there's some use of that here in the US. So I want to make sure that it's not regenerated, one. Two is the source of the carbon itself. So the properties of, say, a coal-based carbon or a coconut-based carbon are going to be different. And so it's not an apples to apples comparison. And lastly, the actual carbon content from a weight basis varies significantly. And so you really can't look at these technologies on a cost per pound basis on the apple to apple, you have to really normalize them based on the carbon content. And so, for example, BOS 200 may have four times or more than 4 times the amount of carbon as, say, another competing technology that's in the marketplace. And so those are the 2, or I guess 3 main points to consider whenever you're looking at, you're entertaining these technologies. So from a lithology standpoint, we work all over North America and in other countries, and so you work in clays and silts all the way to sands and gravels, or if maybe it's a mixed bag site where you've got a little bit of each of those. And so if you've got equal mass and say two theoretical cubes, one's clay and one's sand, the amount of material is going to be the same, because if they have the total mass, the loadings are based off of total mass. And so if that mass is the same, then what's going to be different may be the injection point spacing, which for these technologies is usually 5 to 7 foot on center. We can get as far as 10, but that's pretty rare. The injection volume per interval may change. The actual downhole tooling, the flow rates, all those are sort of the variables that can change depending on the varying geologies. And then we talk about more challenging geologies like glacial till and say weathered bedrock. Now, some of those are accessible with traditional direct push techniques, but some aren't. And that's kind of where our pre-drill process comes in. And I'll touch base on that later in the presentation. And then lastly, excuse me, as I mentioned before, we do some bedrock work. That's not going to be the focus of this presentation. That's got its own breakout webinar. But there we're using straddle packers to isolate fractures that have been identified to contain contamination, to be able to pressure inject the slurries. And then lastly, the carbon technologies work really well with other remedies. And so looking at a combined remedy technique, looking at integrating, even something simple like, excavation, shallow excavation, get rid of, vado smear mass, injecting down below that, surfactants, chemical oxidants, have all been integrated with these technologies. And all the project managers that are at AST we're all former consultants and have been exposed to those technologies and can work with you to be able to develop the best approach for your site. All right, so activated carbon is an awesome platform. That's kind of how we like to refer to it, and I like to think of it as kind of like our cell phones or our tablets, right? And so you can load up different applications onto the activated carbon depending on the situation, depending on the contaminant, for example. And so, like last week, we talked about abiotic and a combination, abiotic bio combination treatment for chlorinated solvents. We're going to focus mainly on bio today as the treatment mechanism, but there are multiple mechanisms that we can use, and using the activated carbon as really just a sorption platform for these degradation methods. And so obviously the first step of the trap and treat is the trap, right? Everybody gets that. That's the activated carbon, sorption of the contaminant into the pore structure of the activated carbon. And so that does a couple things depending on where you are. So if you're in a distal end situation, you're in mainly aqueous mass, carbon's great because it functions just like you would a carbon can on the back end of a treatment system. Okay, you're just polishing what's coming through. Source areas are a lot different because most of the mass, maybe 80–90% as much, can be tied up into the soil. And so how do you use these technologies to clean the source area? And so what you do is the activated carbon is going to first adsorb what's available, which is what's in the aqueous phase. It's kind of the easy part when you're talking about source areas. The sorb phase, which is the larger component, is the much harder, longer term piece of this. And so, but by treating the groundwater, disrupting that natural equilibrium, you get the mass desorbing from soil into groundwater. And I'll show you some data, some long-term soil data here in a few minutes. But the one thing that I'll keep reminding you is that you need to have time for that to happen, especially if you're talking about significant soil mass, because we can't control that desorption rate. Okay. All right, so BOS 200, and so it is consists of activated carbon, and electron acceptors that we load up into the product are nitrate and sulfate. So nitrate's going to get utilized first, obviously. Sulfate's more long-term terminal electron acceptor. Activated carbon has a high affinity for oxygen, and so oxygen gets entrained within the activated carbon during the actual mixing process. You can see there on the right-hand side, those are bags of BOS 200, come in 50-pound bags or 1,000-pound super sacks, and they get added. You can see the eductor and the mix tank there in the background of that picture. So besides the nitrate and sulfate, we've got we got a nutrient package, as well as we add a consortium of facultative bacteria. And I want to spend a few minutes on this. And so number one, this is unique in our industry. And the reason why it's unique is because it's protected with the patents that RPI carries for the BOS 200 product. From a technical standpoint, it's really a key to efficiency. What I mean by that is if you inject all the same ingredients without the bacteria, you're making one big assumption, is that you've got the right bugs in the subsurface to begin with, and secondly, you're going to get the proper bacteria to start to sorb onto the activated carbon surface. So first off, you got to make sure you have the right bacteria, and secondly, it's going to take time for that to happen. Before that happens, you're just relying on sorption, which obviously is not something that any of us are going to want to promote, because we want to be able to make sure that we're applying a technology that's got a treatment mechanism built in with it from day one. And something else that we've been working on over the last few years is what we're kind of tentatively calling BOS 200 plus, and it's BOS 200 with with a food grade electron donor, mainly starch, with yeast extract and an additional consortium to be able to break down that carbohydrate. And this was originally designed for LNAPL sites, and that's where we've primarily used it to date. But we're looking to expand that into other sites as well. And the idea here is that you're giving the bacteria a highly available electron donor to be able to basically boost the bacterial population even more so than we normally do from day one. And so that's going to be really important when we're talking about source areas, but it may have applicability on sites that have really low concentrations as well, where there isn't as much food. So if you're dealing with a 5, 10, 15 microgram per liter benzene concentration, they might be able to use this to help boost the bacteria and supply an electron donor where there really isn't one from a contaminant standpoint. All right, so talk about the proof of concept a little bit. So we've got laboratory mass balance experiments that RPI has been running for many, many years. I'll show you some of that data here in a second. We have states that we work in where we're looking at total mass reduction over time. So we're doing total mass in, total mass out, maybe over an 18, 24 month period. We've also got really long-term groundwater data that really shows that we don't get rebound over time, or the contaminants don't release off the carbon, for example. And replacement wells are also used depending on where you are geographically, or if it's something that if you have a well that cannot be rehabilitated, that's got carbon in it, and it's getting in your samples, then maybe something to consider replacing the well. And we've got some of that data that I can show you here as well. And then lastly, CSIA, or compound specific isotope analysis, is kind of not a new technique, but it's a technique that we're starting to look at more and more, because it's a clear line of evidence of degradation versus sorption. So if you're familiar with that technique, that will make sense. Don't have the time to really dig into CSIA today, given our time frames, but please feel free to reach out if you'd like some more information on that technique, or if you'd like some references for some labs that are currently running it. So if you look at the image on the right, here's an example of soil reductions over time. Okay, so if you look at the blue is 2012, the red is 2015, and the green is 2017. So this is, and I'll show you this was a LNAPL site. I'll actually show you the LNAPL gauging data for the well that is close to where these samples were all collected. And the blue is our baseline. That was our initial RDC. The red, 2015, is when that was post-pilot test. I think as soon as the full scale was beginning to wrap up, and then the 2017 data, the green was part of the closeout process, and the site was ultimately closed in 2018. And so a couple things. One is you look at the magnitude, right? So you're talking about 8,000 milligrams per kilogram of TVPH at a peak concentration. So obviously NAPL. And you can see we got it down to around 2,000 in that zone. But what you have to really look at is the time frame there. You know, you're looking at 5 years. And so if you have these kind of concentrations and excavation's not an option. I mean, if time is critical, maybe something else makes sense. But if you've got time, we've got enough data to be able to support us that we can be effective in soil reductions over time. So this is I love this graph. This is this chart. This is a gasoline bench data that RPI generated. And so they took a 500 milligram per liter spike of gasoline you see in this second column over. Here is your baseline BTEX concentration. So very similar to what you would see in a source area at a UST site. Here's the 3-day concentration, and you see these 80 to 96% reductions. So that looks great, but that's at 3 days. That's straight sorption. Bio has not really kicked in yet. So these are the initial concentrations that these are in line with what we see out in the field. That doesn't tell us the whole story, right? That's just the trap. And you look at these last two columns here, the 30-day and 120-day total mass reduction. So these are when a complete mass balance was done, including stripping all of the remaining hydrocarbons that were adsorbed onto the activated carbon. And so you see at 30 days, we've got a 28 to 50% reduction in total mass, and then 78 to 95% at 120 days. Now these were aqueous experiments, but you can see that so if you're talking about extrapolating this out to a field site, obviously the bench timeframes are going to need to be stretched out a little bit to be able to see these concentration decreases longer over time. But it's a clear line of evidence that we're getting total degradation and not just sorption onto the activated carbon. So this is a really interesting site. So this site has long-term BOS 200 data. So going back to middle of 2015, the solid vertical black line was when the injection work was complete. Before that, some variable benzene concentrations from 15 to up to 50 plus milligrams per liter. If you look at the baseline or the pre-injection concentrations, they were between 5 and 10 milligrams per liter benzene. And this site is interesting because it not only got one well replacement, but it got 2 rounds of well replacement due to some redevelopment that was out on the site. And so the wells were replaced immediately post-injection. And about 6 months later, they had to change the grade of the site. And so they had to abandon the wells and reinstall them, again, with the screen intervals being adjusted to be in the same interval that they were before. And you can see that from the August 15 baseline, we have like a 98 to 99.9% reduction in benzene concentrations. So this is some LNAPL treatment data using BOS 200. So this is the site that correlates with this soil data that I showed you a few minutes ago. This is the NAPL gauging data for that site. So the fonts are a little small, so I kind of blew them up for you. So the groundwater level in meters below grade is on your primary, your LNAPL thickness in centimeters is on your secondary. And you'll see here this line right here where we completed the pilot test. And this is, you see the NAPL, the NAPL levels decrease. We do see some rebound here. Again, this was a limited pilot test area. And these brackets here, these 2 vertical lines are when the full-scale injection started and stopped. And you'll see that we had a 24-month period that's on this graph where we did not see NAPL come back into the well. And actually, this well was monitored for another year. I don't have that data here available, but so we had 36 months before the site was ultimately closed out of where no NAPL was detected. And actually, this was one of 6 wells on this site that had NAPL present. And at the time in 2018, whenever the site was closed, since from the full scale up until the closure point, NAPL had not come back into those wells. Okay, so MTBE, I get this question a lot, or we do, and I wanted to pick a data set to show you where, you know, not all the lines go down, right? Not all the data looks good, and be able to explain why. So MTBE, you know, when Scott in the first session got into activated carbon a lot more and talked about competitive sorption, and MTBE is pretty far down on that ladder relative to something like toluene or xylene. So those are going to sorb, and they're going to preferentially be degraded more than likely as well. So what happens on a site where you have MTBE? And so the guidance that we give is that if you've got significant TPH mass, specifically the substituted rings like xylenes or toluene, for example, those are going to preferentially sorb and preferentially be treated over MTBE. And so if you've got a lot of MTBE and a lot of BTEX, you're going to deal with some of that MTBE. But if you've got a goal for MTBE concentrations that's relatively low, you may have to come back and do some supplemental injection work once that initial, all that BTEX compounds and all those other hydrocarbons have already been dealt with. And so on this site here, you see we had, you can just discount DPE2 for a second. So MW1, 3, DPE4, and 5. The concentrations decreased. These were also areas on site where we did not have significant TPH mass to compete with the MTBE. The one exception was the DPE2 area where there was significant mass. And so the feeling was that's what was out competing for space on the activated carbon, and probably from a bacterial degradation standpoint as well. One point to make is that the consortium of bacteria that RPI provides does have MTBE degrading bacteria in it. This site in particular did not have an MTBE goal. It was really focused on benzene, so we're able to close this site out without going back to do the additional MTBE treatment. But we have had to do that on multiple sites that we've worked on. All right, so talk about conceptual site model development. So I like to say that everything works in a beaker, and so everything works in the lab. So why do things fail when we get to the field? And so we're talking about source areas. Mass distribution in the soil is complex and it's highly variable. I like to say that it scales with the heterogeneity of the lithology, and it's usually underestimated in source area remedial designs. And I've even seen some designs that are based off of groundwater alone, which I don't think most people aren't doing, but some are using groundwater and you running a partitioning model to kind of back into some soil concentrations. I think that's bad practice. I think you've got to have vertically profiled soil data to really understand how that mass is distributed vertically. And the second reason that I'd say a lot of sites fail is just based on contact, and again, that's going to be the focal point for our subsequent webinars. So we call this additional characterization the RDC. And so it's a detailed understanding of the vertical and horizontal distribution of speciated and total mass. So speciated because, we're dealing with activated carbon, we're running sorption isotherm calculations. And so obviously we need to have, benzene data, for example. But total mass is also really important because we have to account for everything. We want to have this, we want to have our designs based off of total mass that is in the system. So we work with our clients, our consultant partners, to be able to fine-tune the existing conceptual site model, fill data gaps, and to be able to come up with a really surgical design. And almost always this additional characterization work is going to pay for itself in the optimization effort. And so what do we mean by detailed vertical and horizontal sampling? So on the soil side, we're usually collecting samples every 1 to 2 feet vertically. On the groundwater side, if we've got long groundwater screens, maybe we're doing nested wells or maybe some sort of groundwater profiling. And we can do this within RPI Group because the RPI Project Support Lab that I plugged early on runs all these analyses pro bono. So it's not, which is unique in our industry. These aren't for compliance. These are strictly for filling data gaps to be able to come up with more surgical detailed designs, but also really helps us manage client expectations. And this was also, this process, the RDC process was called out in the recent ITRC guidance document. If you'd like a link to that later, please reach out to me. And so there's that image that I showed you before. So you get a really good snapshot of what the source area architecture looks like. And we take all of that. So that site that I showed you before that had the multiple well replacements, that site went through an RDC and it got broken down into all these different little sub areas. All these sub areas are broken down vertically as well. So we get the application techniques. Again, this is going to be the focal point of the next webinars, but direct push, top-down progression from our standpoint is really necessary. It's an idea of the flow rates. And so this kind of gets back to the need to have an authorized installer network, because you got to have very specific injection systems that can meet these flow rates. And those flow rates are going to vary depending on geology, depth below grade. The pre-drill technique, which I'll discuss here separately in a minute, is essentially using sonic or augers to get down past that, whatever that refusal is, right? So if it's fill material, if it's cobbles, if it's weathered bedrock, backfill that with hydrated bentonite and then re-drill with direct push. So the flow rates are going to be similar between those two methods. Bedrock is advanced bottom up. The packers, just in case any material sloughs in, you want to do that in a bottom up fashion. The flow rates there can vary a little bit more. And lastly, soil mixing is an option really for any technology. So BOS 200 is used often in excavation backfill. So taking it down to the smear zone and seeding the smear zone to the top of the saturated zone with BOS 200. So this cartoon obviously isn't what carbon or any injectate really looks like in the subsurface, but it gives you an idea of, again, this spacing in an overburden is going to be usually 5 to 7.5 foot on center. Very rare occasions of what, the 10 feet. And we stagger the vertical injection intervals usually between 1.5 and 2 feet vertically. And the injection volumes are designed so that we get some overlap between the adjacent injection locations. There's just a photo of the pre-drill process using a sonic rig. They're the packers. So those are some custom packers that we had built that we'll be discussing in the Bedrock webinar. And then lastly, here's an example of a shallow trench where BOS was applied with sand. All right. So I mentioned the pre-drill technique, and so we're using this more and more. Sites up in the Pacific Northwest, Canada, New England, say where we've got glacial till, weathered bedrock, and states like Pennsylvania, maybe for example, where we've used this technique a few times. Historic fill, places like New York City, for example. And so it's you're using augers or sonnet to get down to your total depth, you're backfilling, and then you're re-drilling it. Now you can use this technology for that because you can think that it's kind of like a pressure washer coming out of that injection tip. Those injection fluids cut through the bentonite and get out into the native formation. So we've got about 35, maybe close to 40 sites now where this technique has been used. Recently, we completed a project down to 180 feet at a Department of Defense site in South Carolina. All right, so we'll go through a few project summaries here, and then we'll go ahead and open it up for Q&A. So this is a pre-drill project summary. So the initial work was done in 15, and then full scale later that year in 15, and then the PRB was extended in 2017. So this is up in the northeast U.S. at a rest stop, and the site was brought up to grade with about 20 feet of construction debris, so not very direct push friendly. And the goal was to set the PRB up so that we could protect the wetlands that sat to the north. And each location was pre-drilled down to bedrock using sonic. And so it was about 150 feet long. We had 88 injection locations on a 7.5 foot spacing approximately. And the injection interval was from 26 feet to 34 to 57 feet, depending on where bedrock was encountered. And so you'll see here we've got MW204. This is our up gradient well. This MW205 that you see in the middle was our pilot test well. It got consumed by the full-scale PRB, so MW207 was advanced to give us a better down gradient monitoring location. So you see here the blue is the total BTEX coming in. The dashed vertical line is the pilot test. The solid is the full scale. And so you can see that, you know, our initial concentrations were, you know, up gradient close to 1,000, down gradient close to, say, call it 1,600 ppb. And since the full scale implementation, we've been able to keep those down. Had a really small blip here corresponded to this increased flux coming from the concentrations here, but that did come back down. And so we're about 1,000 days post pilot test. One thing to keep in mind when you're dealing with bio PRBs is you got to keep an eye on the thermal electron acceptors, which is something we're doing out there. Those pre-drill locations that are on this picture you can see here, the reason why they were completed at the surface is that so we can come back at a later time to be able to supplement with additional thermal electron acceptors. And lastly, I'm going to wrap up with this. I do have one more project summary, but I'd like to get to the Q&A, and I'm kind of running out of time. And so if you're interested in more project summaries, we just on our new website that we just launched, we've got quite a few. And the second site, which is a pipeline release site in Michigan, another long-term BOS 200 project, we've got that written up as a project summary. So I'll wrap up here with this slide. And so I mentioned CSIA being used on one of our projects, and we've got some other projects that are in the hopper where it's going to be used. But they collected samples along the center line through the PRB down through the plume, and they were able to determine that there was isotope enrichment as compared to the up gradient well, which was MW204 for N-propylbenzene, ethylbenzene, MP xylenes, and 1,2,4-trimethylbenzene. The only outlier was that there was not enrichment for O-xylene. So we were able to determine, or our client was able to determine that enrichment, which indicates bio is taking place, is occurring within the PRB, and that was demonstrated down 80 to 100 feet down gradient from MW204. So again, I'm going to skip through this last, and I'll open it up. If my moderators want to jump on, we can start the Q&A. Thank you for your time.
All right, thank you, Mike. This is Derek Pizarro with AST Environmental. I'm also going to bring in our president, Dwayne Guilfoyle, for our Q&A session. I have a couple questions here, so I'll get through them. If you can stay, we'll get through all of them. And if there's too many, we'll reach out to you individually at the end and answer those questions as well. So I'm going to be asking Mike and Dwayne. First question is BOS 200 on the general WDR for California?
If you're, I'm assuming the question is for, each water board is different from the way that I understand it, and we're going through the process in Los Angeles right now, but we have applied BOS technology. We've applied BOS 200 specifically in San Diego County and the general Bay Area, including Sacramento. So, but we are working through the process right now to get BOS 200 approved on the revised reagent list through the LA Water Board.
All right. Next question. Do you recommend NAPL recovery prior to injection of BOS 200?
Absolutely. Absolutely. I think that's if you want to remove as much recoverable NAPL as possible. And I've had clients that have actually done enhanced fluid recovery post injection. So because BOS is a solid, you're not going to pull it out, and because you are kind of reshuffling the deck in the subsurface to a certain degree because you're putting a lot of energy into the subsurface, you can actually get greater recovery rates post injection than prior.
Okay, and this is kind of a corollary to that. Could I achieve MCLs if I'm starting with ppm level concentration?
Well, I mean, that's that's a complicated question to answer. It's really going to be tied to the soil mass. One injection is tough for most technologies. If you're talking about, if you're starting at 5 ppm benzene and you've got to get down to, low ppb levels, we have done it, but it's really going to depend on what that soil mass contribution is. So if you've got considerable soil mass, so if you look at your aqueous to sorbed ratio, how much mass you have, if you've got 10% aqueous, 90% sorbed, it's going to be tough to do that. But if it's primarily in the aqueous phase, then I think it is doable with one injection.
Yeah, to add on to that, Mike, a lot of it too gets into contact as far as the distribution, as far as the installation. So, on geologies that are difficult, and the QC on the upfront side just to verify distribution, and really, we know that the product's going to work. Our product's powerful. It's in a lot of cases to get down to for instance, like New Jersey or someplace where you've got a 1 ppb standard, then a lot of it's going to get down to the actual distribution and installation of material.
All right, thank you both. Let's kind of stay with the analysis side of this. I have a question here. You refer to performing TPH analysis during the RDC. Why do you need this when most states are not regulated by TPH requirements?
Well, I mean, you can draw the corollary with something, say, like chemical oxidation, right? So chemical oxidation is not specific, and bacteria the same way, right? And so we've got in a chemical oxidation scenario, what's the analyses you have to run? It's total oxidant demand. Why do you run that? Because you have to account for everything. It's the same thing here. So we've got to account for all the mass, and it's got to be speciated too, so that's the point. But so we've got to know, for example, how much benzene is in groundwater, how much is in soil, but then also how much TPH mass is in groundwater versus how much is in soil. Because when we run our designs, we're looking at the speciated compounds, but we're also looking at the overall TPH mass to see what's going to be the limiting factor.
Yeah, I agree with Mike. I mean, it's especially when you get into these sites where you've got significant mass, and people often ask us, they'll send us data on sites. It's an LNAPL site, and without saturated soil mass data, specifically total TPH, really hard to understand how much total LNAPL or how much mass is in the formation. So I think a lot of the states are starting to recognize the importance of that data, even though it's not regulated, but they're starting to recognize how it drives the overall performance and I guess the evaluation of the site itself, for the amount of time that it's going to take to actually get to the cleanup standards.
So I'll tie in on that comment, Wayne. There's a couple questions here. I'll try and distill them into one. Based upon what you just said, is there a way to speed up time frame for mass reduction? And is that what you're using the activated carbon for?
Yeah, so some of that speed is driven, like Mike touched on this, and if you went back, Mike, to the slide on the soil mass removal over the 5-year period of time, well, the zone that took, and I'm really familiar with that project, the zone that took the 5-year period of time to reduce from the 8,000 to the 2,000 ppm concentration is in the smear zone. So, Mike talked about this from the overall concept of technology is that, the transport mechanism is groundwater. And so in the smear zone at that site, that zone was not saturated 100% of the year. So, you don't have intimate contact and the overall absorption of the mass into the groundwater and onto the activated carbon. The power, though, that is the product once it's in place that it's going to continue to manage that mass. Now, in areas like sites that are saturated and really you're not limited on how fast the contaminant is getting onto the activated carbon, then yeah, you can speed up the treatment of a site, and that's by providing additional platform for treatment, which means installing more carbon. So the larger the carbon platform, the faster of that overall degradation of the site, and that gets into a kinetic design that I think Scott Nolan talked about in his first on the initial webinar. So the speed of that degradation we can speed that cycle up. It just means putting more carbon in the ground.
All right. And then we've got a couple questions here on PRBs I think it'd be nice to close with here. Regarding PRB use, how long will they last without maintenance? Do they require maintenance? And are there potential biofouling issues?
Well, so it's all going to depend on, number one, the mass flux, or the flux coming through that cross section, right? So we've got a certain amount of, say, sulfate that we can load up into the barrier, which is going to be your long-term terminal electron acceptor. Well, that is going to be utilized over time. You're also going to get that advect out of the PRB zone. That's going to be a function of the flow rate coming through that cross section. So, I would say, a year and a half to 2 years, probably 2 years closer, in a relatively low seep velocity situation. However, if you've got enough, and this is where the sort of baseline information is really important, I've seen sites where the baseline sulfate concentration is over 100 milligrams per liter, which is more than enough to feed the biological processes within the barrier itself. So you may not need maintenance, but if you do, I would say it'd be on a 2 to 3 year time frame. Dwayne, do you agree with that?
Well, I mean, you gave an example there, Mike, on the site, up in the Northeast that the BOS 200 PRB's been in place for, 1,000 days or more now, and it hasn't required additional terminal electron acceptors to support it. And I agree with Mike. I think that there's a lot of PEAs in the formation that can be utilized by the bacteria, in addition to, the sulfates and the nitrates. So it's like Mike said, it just depends on what the natural conditions are. There may be enough there to support, for the low concentration flux that some of these PRBs that are dealing with. Now, related to the biofouling, Mike, you want to comment on that? I mean, you know, we've installed this product for the last 15 years and dealing with source treatment, and whether that also be transferred over into PRBs. And we have not seen issues with biofouling related to these sites. The performance continues to improve. Saw long-term data from the site over in Finland that Mike showed you that had the 2 wells that were replaced over, and that continued to degrade over time. And there's not an issue with biofouling that we've seen on any of those sites.
Yeah, and I guess just to add to it, we've done, enough work in the lab too, where, we've run, say, column experiments and with a high pore volume exchange, and we haven't seen a, increase in pressure over time going through the column. And so that's an ex situ sort of, sort of verification for what Dwayne just described. But the bacteria, as they grow, they're going to reach, they have a, kind of a, cycle of life. And as they die, they're going to slough off, and you're going to get new bacteria to take their place. But, as you think about how that injection cartoon that I showed you before, we're not influencing 100% of the cross section in any one given area, which is why like multiple rows, tight spacing, multiple rows is really important. But you got to think that we're trying to achieve contact across that barrier, but that barrier might be 20 feet, 20 feet thick. So it's not like all the carbon is going in one place, within one small strip, where I think that may be an issue. That's not really how they're installed.
Well, thank you, Mike and Dwayne, for the Q&A session. I will mention to our attendees before I turn it back over to Mike that there are actually a good number of questions here that happen to pertain to RTC and installation. We will reach out to you individually to answer those questions, but I would also encourage you to visit our next 2 webinars that will cover some of the questions that have been asked here. But we will take the time as a team to reach out to you and address those in the interest of time. So, Mike, the floor is yours, and thank you for a great presentation.
Thanks, Derek, and thank you, everyone. I understand your time is valuable. Stay safe. If you have any questions, please feel free to email me or Bob Elliott, Bob at Trap and Treat, or Mazaris at AST ENV. And we look forward to speaking to you next time. Thank you very much.